Hello and welcome to this video in which I want to introduce you to distributional transformation and its application to predicting chronological age from structural brain images. So often in machine learning, the challenge is to predict some target values, also called labels, from a high-dimensional set of source variables, also called features. This problem is called regression, and target values often fall into some natural range in which their values must be. This is true for chronological age, which is typically between 0 and 100 years, but it also applies to IQ, body height, body weight, and especially frequencies and probabilities, which typically must be between 0 and 1, but which are not preserved to be in this range by each machine learning algorithm. So in order to solve this problem, we propose distributional transformation. Distributional transformation takes a set of predicted target values and transforms them to the distribution, to the observed distribution of labels in the training data set, for example. This then ensures that the transformed target values have the same distribution as the labels in the training set. And this can be applied to other predictions as well. So mathematically speaking, we are taking observations from a random variable x, and we use the inverse cumulative distribution function of another random variable y to transform observations x into other observations x tilde, which are guaranteed to follow the same distribution as the random variable y. Here we apply this to predictions in a test data set, y2 hat, and we use the inverse CDF of labels in the training data set to come up with adjusted predictions y2 tilde, which have the same distribution as the labels in the training set. In our study, we apply this to brain age prediction, where one typically has one high-dimensional structural brain image of brain structure measurements. And the goal is to estimate the chronological age of each participant. These data were part of a predictive analytics competition. And for this purpose, the dataset was split into training and validation data, where the validation data were unknown to the participants prior to the competition's end. Here I'm showing labels and features for training and validation data. On the left, you can see vectors of chronological age for each participant. And on the right, you can see design matrices containing regressors for dimensionality reduced gray matter, dimensionality reduced white matter, and confound regressors for site and sex of each participant. We used multiple linear regression, in which age was used as the dependent variable, and gray matter, white matter, site, and sex were included as independent variables. We also applied support vector regression, where gray matter, white matter, site, and sex acted as features, and age was used as the target variable. Finally, we used deep neural network regression with the same setup and settings, details of which you can find in the paper. So if we are looking at plots of predicted versus actual age, we can see that the highest Pearson correlation and lowest mean absolute error is achieved when using multiple linear regression with distributional transformation. The metrics were worse for support vector regression. And while linear regression and support vector regression benefited from distributional transformation, the mean absolute error actually got worse for deep regression. The same tendencies and trends were also observed when checking metrics other than Pearson correlation and mean absolute error. Finally, when having a look at the predicted age distributions, we see that the distributions were all significantly different from the distribution of labels in the test set. But this distribution was markedly lower for deep regression, as the distribution of predictions was already quite close to the observed distribution in the training data. After distributional transformation, we see that they all have the same minimum KL divergence possible with our level of discretization. And finally, here in the bottom, you can find transformation functions when moving from unadjusted to adjusted predictions, which kind of reflect the distributions before and after distributional transformation. So with that, I want to say thank you. And if you want to know more, feel free to check out the paper, which is available open access. So thank you very much.